Hello and welcome to another lecture for my class, PSYC 440/640. The class is called Experimental Methods, but is really more of a class on univariate data analytic techniques from a model comparisons perspective. As usual, I'm starting with a web comic. This is from xkcd.com and really has no bearing on the rest of the lecture other than that we're at that point in the semester where I feel like my brain has been taken over by fungi and I don't know, I'm sort of looking forward to the end of the semester, which is no reflection on my students or my colleagues. I just get kind of worn out by this point. And not to sound too worn out any more than I suppose I already do, but this lecture is just yet more stuff about ANOVA, talking about some features of Oneway ANOVA. The class is called 23.5 because I used to combine this with a bit of an introduction for ANCOVA. I'm putting that in a slightly separate lecture. So this will be, relatively speaking, I hope, a short lecture, and it'll just finish up some of the topics that I've addressed on in Oneway ANOVA. So by way of an overview, I'll continue talking a little bit about contrasts and trends, talk briefly about post-hoc tests and effect sizes, and along the way we'll have a bit more practice with Oneway ANOVA. So talking about contrasts and trends, talking about slices of cake. Here's a delicious looking red velvet cake, I suppose. Anyway, a point that I've made a few times across this the last few lectures is that usually you should plan your own contrasts. You should take advantage of coding schemes either using SPSS syntax, or I prefer using coding for dummy code variables or contrast code variables in regression to plan contrasts that allow me or allow you to test hypotheses that you care about, rather than just willy-nilly comparing all sorts of different levels of a given predictor variable. Again, we should do contrasts that are based on hypotheses that we have. Sometimes we can take advantage of standard contrasts that exist in SPSS. These are kind of classic ways of doing comparisons, which have been used so much that stats packages like SPSS will offer them kind of as an option within different modules, notably within the GLM module of SPSS. So sometimes we can use these, and when possible, by all means, take advantage of them. This is a rather big table. It just details some of the different contrasts that are available as kind of standards in SPSS. The ones that are probably the most familiar to people will be the simple contrasts. Simple contrasts are basically like the type of contrasting we do with dummy coding, where we have a particular level of the predictor variable, which serves as a baseline or comparison for all the other levels. And SPSS allows us to designate either the first level of our predictor variable to be that comparison level or the last. So if it's the case that you have a predictor variable which has a control group or like a baseline group which either occurs in the earliest position in the sequence of levels or in the last position, then you can, if you want to, just ask SPSS to do simple contrasts. The other one that may be familiar are the Helmert contrasts. Helmert contrasts are a lot like the contrasts I've shown you using contrast coding. That is, we're taking one level of a particular predictor variable and comparing it to averages of the subsequent levels. So for instance, level 1 of a predictor variable compared to the average of level 2 and 3, and then level 2 compared to level 3. Or if you had 4 levels, as you can see kind of towards the right, you might compare level 1 to the average of 2, 3, and 4, then level 2 to the average of 3 and 4, and then 3 to 4. This is somewhat more common sometimes in studies where the predictor variable has a kind of a dosing relationship, like I've described in the various drug and kind of pharmacology examples that we've used, where you're kind of successively comparing higher levels. There are others, as you can see. Repeated contrasts are, I think, sometimes familiar. You're just comparing each level to its previous level. That sometimes makes sense if we have kind of a natural ordering that supports that, I suppose. It's worth noting that some of these are orthogonal, for instance, Helmert and reverse Helmert, sometimes called difference, and many of them are non-orthogonal. Not that that means you can't use them, it just means that they are, they have certain considerations that you might want to keep in mind. For instance, the fact that those contrasts, those comparisons will be correlated with each other, which can, on some circumstances, present some interpretive problems. Another option you have in SPSS is kind of a standard are polynomial trends, or sometimes called polynomial contrast. These are just ways of doing contrast coding that allow you to look at specific shapes, if you will, that occur across successive levels of a predictor variable. So for instance, you can look at a linear trend to see whether the outcome variable changes in proportionate steps across levels of a predictor variable, or a quadratic trend, which allows you to see whether that change occurs in one direction and then shifts into another, if there's kind of like a kink in the line. And a cubic trend is sort of the same idea, except there are two sort of shifts or kinks in the line. If that's a little bit difficult to visualize, here is an image. By the way, this image and the previous one are from Andy Field's textbook, Discovering Statistics Using SPSS. And you can see here that we've got, in each example, 5 different levels of our predictor variable, whatever those happen to be. And you could see if there's a linear trend in the outcome variable across those, or a quadratic or a cubic or even a quartic trend. It's probably obvious, but if it's not, I'll make the point right now. This really only makes sense if the predictor variable, if the levels of the predictor variable have a meaningful natural order. So if your predictor variable is something like dose of a drug, and each level is like an increment of 25 milligrams, then of course it might be very interesting to test the linear trend, or to see if successively higher doses of the drug yield successively higher drug effects, or maybe like a quadratic trend to see if at some point there's diminishing returns and the increase in drug effect kind of levels off. If you have a predictor variable where the levels don't have a natural or sensible order to them, like if those 5 different levels were just like 5 different racial or ethnic status identifications, then it probably doesn't make any sense to imagine or to test, well, is there a quadratic trend across these levels, or a quartic or cubic trend? It's often the case that we don't get a lot of use out of these types of trend analyses, again, unless we have predictor variables which have kind of a natural ordering or dosing type relationship across their levels. I should say also at this point that if you've watched my supplemental video on coding for contrasts, I talk about how you can accomplish these type of polynomial coding contrasts using coding much as you would any other contrast coding. There's not anything really fundamentally different about them, and I go into some more detail in that video as to how you might do them using a kind of a contrast coding scheme if you're using the regression module. For the time being, though, we're going to eschew the regression module, and we're instead going to focus on the Oneway ANOVA module, in which you can see in SPSS here. And by the way, if you're enrolled in my class, this is the example where we're using the Viagra 4 data set. This is essentially the same sort of data as we had in the other various Viagra data sets, which I originally got from Andy Field's Discovering Statistics Using SPSS textbook. You can download those data sets for free from the book's companion website. The only thing that's a little different here is I tweaked some of the levels of the outcome variable in one of the groups to kind of exaggerate what you'll see in a few more slides as a trend effect, or like a trend contrast. So what we're going to do in this example right now is we're just going to run an analysis using the ANOVA module, as you can see, and we're going to ask for some polynomial contrasts using the contrast button, or the contrast menu here. So this is just an example of how we can use the Oneway ANOVA module and get some contrasts that are maybe a little bit interesting to us. We're going to click the checkbox for polynomial, and we're going to select the degree of the contrast, the polynomial contrast that is that we want. And polynomial contrasts are ordered such that if you ask for a quadratic contrast, for instance, you'll get the contrasts beneath it in order. So beneath quadratic is only linear. But if we had enough levels to support a cubic trend, we could ask for a cubic trend, and then we'd also get quadratic and linear as well. So they're kind of ranked in those that sort of power order. Anyway, so select polynomial contrast, select quadratic. Then for options, we can ask for some descriptive statistics and a means plot. There's some other things here: a homogeneity variance test, Brown's, Forsyth, and Welch tests. I'll talk about those a little bit later, but you can click on those if you want. Once you've selected all that, hit continue, hit OK. So here's some of the output we get, and it looks more or less the same as the output that we've seen previously from SPSS. The obvious addition here is that we have tests for a linear term and a quadratic term. We can see that the contrast for the linear term is significant. The p-value is less than 0.05, and we can interpret that as suggesting to us that the outcome variable, libido, increases proportionately across levels of our predictor variable. And again, this really only makes sense if it makes sense to think about those levels of the predictor variable as having a kind of an ordered and proportionate relationship to each other. And in the case of a drug study with dose being the level, then that kind of makes sense. You can also see that the deviation is significant. We can interpret that as suggesting that the outcome variable increases in a non-proportionate way across those levels. So it's almost like a contradiction of the previous point I've made. The interpretation here would be that the trend could be non-linear in nature across those three levels. Moving on, we can see that the contrast for the quadratic term is significant. Again, p is less than 0.05, and we can interpret this as suggesting that the outcome variable increases in a quadratic fashion across levels of the predictor variable, or put more simply, there's kind of a kink in the line that goes across those different levels. Now, you've almost certainly noticed here that the test for the deviation for the linear term is essentially the same, or is exactly the same as the test for the contrast in the quadratic term. That's because there are only three levels of our predictor variable, and so the line, a line that passes between the means of all of these levels, can either be straight or it can have one bend in it. Those are really the only two options. So the only deviation from linear is quadratic. That's why those are the same. And if you're having difficulty visualizing it, here is that means graph that we asked for. And again, I kind of fiddled with the data a little bit just to exaggerate that polynomial contrast. So again, it's reasonable to say that in a sense the level of the outcome variable increases across levels of the predictor variable. That would be the linear trend, but it's probably better to say that that increase is quadratic in nature. There's this kind of kink in the line. So if you wanted to interpret this, you might say, well, at a low dose or even a placebo dose of the drug, there really isn't much effect, but once we get to a high dose, there's quite a large effect. There's quite a sudden increase at that point in the dosing. Okay, I know I didn't talk too much about polynomial contrasts or the standard contrasts in GLM or in ANOVA in SPSS, but don't worry, I'll get back to those a little bit later. I want to move on right now, though, and talk a little bit about post-hoc testing and what the options are we have in the GLM module and the ANOVA module. Now, to put this in context, post-hoc tests are used when we want to compare all groups to each other. So each level of our predictor variable, we want to compare to each other level of the predictor variable. We're doing all the pairwise comparisons. And as you remember, hopefully from previous lectures, a problem with that approach is that family of tests, depending on how many levels of the predictor variable there are, can be quite a large family, and the family-wise type 1 error rate might be unacceptably high if we just go ahead and do all those tests without doing anything to adjust for family-wise error rate. And really all post-hoc tests, or almost all post-hoc tests, are just ways of managing family-wise error rate across large sets of multiple comparisons. So again, we want to control family of wise error rate. We don't want our type 1 error to creep up too much across a family of pairwise comparisons, because we don't want apparently significant effects to be false positives, or we at least don't want the likelihood of false positives to be much higher than about 0.05, which is our pretty typical level of alpha that we think of when we're doing psychology research or many other areas of research, I'm sure. But at the same time, we don't want to lose too much power. You could imagine developing a post hoc testing procedure that was very, very conservative, that really kept your alpha level quite low. Even though you're doing a very large number of tests, that would be good in some respects, but it might be so conservative as to lead you to miss potential true effects. You might have false negatives or misses to contend with. So as is often the case, in a lot of statistical testing, at least the type of testing we do for hypothesis testing, there's this balance between type 1 error rate and 1 minus type 2 error rate, which is power. To say that a slightly different way, let's just remember that type 1 error rate alpha and type 2 error rate beta are linked for a given sample size and given effect size, and they're linked in the sense that they have an inverse relationship. As alpha goes down, the test gets more conservative. As beta goes up, the test gains more power. Here's my attempt to visually represent that. You can imagine a conservative post hoc testing approach is one that really keeps alpha low. That's good, except beta then gets rather high, and 1 minus beta is power. Power gets small, or it gets low as well. Another testing approach might be very liberal. It might allow alpha, type 1 error rate, to creep up quite a lot. That's bad, but in a sense it's good, because that means beta is going down and 1 minus beta, power, is going up. So again, there are a lot of approaches to post hoc testing, but I like to think about them in this way. Fundamentally, are they relatively liberal or relatively conservative? And SPSS offers, at last count, something like 18 or more different options. I'm sure there are many, many more out there. I kind of divide them into 3 broad groups. There are some which I consider relatively conservative, like the Bonferroni correction, which I'm sure is familiar probably to most people. There's some which are relatively moderate or balanced. You can see a few of them named there. And there are some which are more liberal, which offer little or even no control in terms of, for example, the LSD test, in terms of type 1 error rate across a family of tests. So we can think about post hoc tests in terms of their relative liberalness or conservativeness, but we have to keep in mind that just like pretty much all tests, post hoc tests really depend on sets of assumptions, and sometimes they'll be robust to violations of those assumptions, but often they're not, and we have to kind of think about that much as we would think about any other testing procedure. Performance depends on assumptions, and post hoc tests are, well, there are a lot of differences, but generally, let's say post hoc tests are not very reliable to violations of the assumption of homogeneity of variance. So if you had groups, you had levels of your predictor variable that differ significantly in terms of their homogeneity of variance, many of the post hoc tests that you could get from SPSS are not going to be particularly robust or particularly reliable under such a situation where variances are quite different. There are a few tests which are designed to handle those types of situations, and of course those types of situations get much worse if the group sizes are unequal. So a really worst case scenario, I suppose, would be something like having a predictor variable which has different levels. The levels have different variances, and the groups, the sizes of the groups that make up each of those levels are also different. You might well want to do a series of pairwise comparisons, comparing like level 1 to level 2, level 2 to level 3, level 1 to level 3, and so on and so on. But because of violations of assumptions, particularly homogeneity of variance and different group sizes, you might have a hard time really knowing how liberal or how conservative are the post hoc tests that you're choosing. So again, I said there are some cases that are designed to handle situations like this. I've tried to recollect and name a few of those. I think if you poke around through the SPSS help menus, you can find some descriptions of these different tests, and certainly much more information about them abounds on the internet. If you sense that I'm being a bit vague about all of this, it's because I don't use post-hoc tests very much, because I like to plan my analyses. I like to do as few tests as possible and really tailor those tests to specific hypotheses that I'm interested in for my research. This allows me, hopefully, to keep the sizes of my families of tests pretty small, so I don't need to worry as much about family-wise type 1 error rate. So I kind of avoid the whole issue. When I do post hoc tests, this isn't probably the best way to approach them, but I try and pick a couple different post hoc tests, like pick a conservative one, a relatively moderate one, and a relatively liberal one, and see if there's kind of a broad consensus across a set of them. And I always try to check assumptions, which is something that I should be doing anyway, and you should be doing as well. So not a great description of post hoc tests, but one that fits my level of interest in them, or I guess more fair to say my level of use of them. So those are my guidelines, or my opinion. All right, well, enough of me talking. Let's do some doing. Here is yet another permutation of the Viagra data set. Again, if you're enrolled in my class, you can access this pretty easily. What we're going to do here is just quickly review some of the topics that I've covered in this lecture and previous ones as a bit of a finish up for Oneway ANOVA. So what do I want you to do? I want you to run a Oneway ANOVA in the ANOVA module. As you can see right here, before hitting OK, I want you to ask for contrasts. These are contrasts which correspond to the Helmert contrasting procedure, or the standard Helmert contrast that we've done before. Using the contrast menu, I'm entering codes, as you can see there, to compare first the placebo dose group to the average of the low and high dose group, and then to compare the low dose group to the high dose group. I'm also, as you can see, asking for a test of a quadratic polynomial trend, which will also necessarily give me a test of a linear polynomial trend. And I'm also going to ask for some different post-hoc tests. And to be perfectly honest, when I made this PowerPoint, I think I almost haphazardly chose some different tests. But you can see here that some of the tests or the tests are organized such that some of them assume equal variances, like I described earlier, and a few of them have been designed so as to not assume equal variances. And as you can see, I've selected a few here. Also, before hitting hitting OK and running the analyses, let's open up the options menu, ask for some descriptives, ask for a means plot, ask for homogeneity of variance tests, and ask for Brown, Forsyth, and Welch tests as well. I guess I haven't really talked about this too much before, but I think that the descriptive stats and the means plots are just handy for visualizing effects, so getting a sense of how the outcome variable changes across levels of the predictor variable. I think that's important, especially if we're going to interpret a polynomial trend. We have to sort of know what it looks like. The Levine's test is a kind of standard test for the assumption of homogeneity of variance. I'll talk about that a little bit in this lecture and in future lectures. And the Brown's, Forsyth, and Welch tests are kind of like alternatives to the F statistic, which can be used in situations where the assumption of homogeneity of variance has been violated. So, just for fun, let's select those as well. So once you've done all that, you hit OK, you run your analyses, you probably get a fairly large amount of output. Here are some of the features of your output. You'll get some descriptive statistics. Those are kind of nice. You can see the kind of non-overlapping confidence intervals suggesting where group differences will be significant and where they won't. So for instance, the placebo dose group overlaps quite a lot with the low dose group. Probably not going to be a significance between those two. Might be a significant difference between the low dose group and the high dose group because there's a little bit less overlap there. It's kind of hard to eyeball that table and know for sure. Here's the means plot. Again, gives us a sense of the differences between those two three different levels of our predictor variable. One little warning I'll make, and I might have mentioned this in previous lectures, is that SPSS tends to scale the y-axis, the axis which records the outcome variable, in such a way that it kind of exaggerates differences. More than once I've looked at a means plot generated in SPSS and thought, oh wow, look, there's this huge difference between group 2 and group 3 or whatever, and then I'll sigh and look over at the y-axis and realize that it's scaling in increments of 0.2 of a unit. Now, of course, it depends entirely on what your outcome variable is. Maybe 0.2 of a unit is a huge difference, but in our situation here, well, it's fake data, but let's imagine that half steps, half point steps are really not big steps in the scale that we're using to measure our outcome variable. So bottom line is, take a look at the chart, but as you should always do, take a look at the y-axis so you make sure you understand how big these differences are before you get too excited about them. Moving on, here's the homogeneity of variance test that we get. It's the Levene's test. Here the test is not significant, suggesting that the variances across the different groups are not significantly different. Now this is the point where I should remind you and remind myself that the group sizes in this fake data are ridiculously small. So one, we probably should never really even do this analysis in the first place, and two, tests like Levene's test are going to tend to be pretty underpowered in small samples with small group sizes. In a way, there's almost that irony that where you care about differences in variances across groups the most is when sample sizes are really small. But those are the very situations where tests like Levene's test are the least able to detect significant differences. When you have a really large sample with really large groups, then you care a lot less about differences in variance, and that's when your test, like Levene's test, tends to be a bit overpowered, and you can see apparently significant differences on it. Suffice it to say for this example, though, if we saw this result for this Levene's test and it's not significant, we're probably feeling pretty good because we think, the variances across these, or I should say the variances within these different groups are almost certainly a little bit different from each other, but they're not different enough to make us think that it's a significant difference. Were we to be too worried about this, we could use, instead of the F statistic for our ANOVA, we could substitute in the Welch statistic or the Brown's-Forsyth statistic, which you can see here work basically the same way. You get a value for the test statistic. It's got 2 degrees of freedom associated with it, as to say a numerator and a denominator degrees of freedom, and it's got a p-value. So under the Welch test, maybe the effect of dose is marginally significant. Under the Brown's-Forsyth test, it is statistically significant. Now, one last point here. This whole idea of detecting or looking at differences in variance, looking for heteroscedasticity, is especially important when group sizes are different. And I don't think they are in this case, although again, I've come up with so many different permutations of this data set, I actually forget. But let's remember, the worst case scenario would be having a relatively small sample with relatively small sized groups making up that sample, and having those group sizes be unequal, because then, gosh, if there are violations of the assumption of homoscedasticity, it can become very challenging to feel really comfortable in interpreting the results of our ANOVA. So just another warning there, and another bit of gentle advice to, when possible, recruit large samples and retain equal group sizes. Moving on in our output, we've got our ANOVA table. This looks much like the ANOVA table I previously showed you, except this time I think the data wasn't fiddled with to exaggerate the polynomial contrast. And yeah, you can see that the linear contrast is significant. The quadratic contrast is not significant. So we got our test of between groups and within groups variance, and then our linear contrast and our quadratic contrast. So overall, the model is significant. We can interpret that by saying group membership or dose of the drug explains some of the variance in libido. Like I said before, it looks like the linear term is significant, so we can interpret that as suggesting that the outcome variable libido increases proportionately across levels of the predictor variable. The deviation is not significant, suggesting that the increase isn't non-proportionate or non-proportional across levels of the predictor variable. So the trend is linear, it's not non-linear. And at the risk of just beating a dead horse here, the quadratic trend is not significant. So once again, giving us the sense that the polynomial trend is better characterized as linear than it is as quadratic. And as I said before, you may notice that we have the same sums of squares and degrees of freedom and mean squares for the deviation of the linear term and the contrast for the quadratic term. That's because with only 3 levels of our predictor variable, there's only one way for our trend to be nonlinear, and that is to be quadratic. And in this case, it's not, or at least we don't have evidence that it is a quadratic trend. If you asked for those contrasts, you'll get a little contrast coefficient table here. This is just a place for you to double check your work, because if you get your contrast coding wrong, it's going to affect how you can interpret the results. Here we got our contrast tests. The ANOVA module, the one-way ANOVA module, nicely gives us tests under assumptions of equal variances and under assumptions of non-equal variances or unequal variances. In this case, it's not a big difference, probably due mostly to the very small sample size we have. If you're interested in what these value of contrast, what that means here, that's just the sum of the means for the different groups multiplied by their respective coefficients. So if we looked at the you can see here in this little equation at the bottom, I took the means for the placebo, the low dose, and the high dose group. I multiplied them by their respective contrast coefficients for that first contrast, and I get that value there. It happens to be 3.8. That's the value that's tested in that first contrast. And you could do the math to get the second one if you want. Actually, I didn't do that here. If we think about these plain contrast, it looks like contrast 1 is significant. The placebo group differs from the low and high dose group. That's no surprise at this point because we've seen that a bunch of different times in a bunch of different ways. Contrast 2 is not significant. The low and high dose group did not differ significantly from one another. You might be wondering at this point, what about one-tailed tests of significance? So far, we've been just looking at two-tailed tests of significance. Of course, this depends on our hypotheses. If we hypothesized that our outcome variable libido would increase with these different doses of the drug, and it's reasonable that we might have made that hypothesis given our understanding of how this drug works, then we might feel justified in doing one-tailed tests of significance rather than two-tailed tests of significance. If we wanted to take that path, all we need to do is divide the p-values for each of these contrasts by 2, of course yielding smaller values, and under that approach to testing, contrast 1 is of course still significant. And contrast 2 is significant because 0.065 divided by 2 is less than 0.05. So we might reason that the high dose group is significantly different from the low dose group if we did one-tailed tests of significance. And as I've mentioned before, this is not something we should decide after the fact, like, oh no, we didn't see a significant effect for that second contrast. We really wanted to. Let's do a one-tailed test. This is something that you should plan out ahead of time, much as you should plan out really all your analyses. You should say, what are my hypotheses? How do I best test them? And if your hypothesis was directional in nature, that is, the drug increasing the effect on the outcome variable, which, seems reasonable, then yeah, totally do a one-tailed test. You'll have more power to detect an effect, and it's probably worth doing. Here's a huge table of multiple comparisons. These are all the different post-hoc tests that we asked for. I won't talk about them too awful much. You can kind of see, if you squint and look very closely, which groups are different from which are significantly different from which other groups under different tests As I suggested before, I don't do a lot of post-hoc testing, so I tend not to pay a ton of attention to this stuff, but just be aware that if you wanted to do post-hoc tests to evaluate multiple comparisons, you get some output that looks a bit like this. Okay, just to wrap up this little relatively short lecture, let's talk briefly about effect sizes. Now, the ANOVA module that we've been playing with just recently in this lecture has a lot of nice features in it, but one thing it doesn't have is it doesn't provide or at least automatically, it does not provide a measure of effect size. Well, that's not too big a deal because we can easily compute R-squared, which is also known as eta squared and is also known as the proportional reduction of error. That's just gives us a sense of how large a reduction of error we get when shifting from the compact model to the augmented model. And it's computed, as you can see right here, and hopefully as reminds you of way back in Unit 1. If we take the sum of squared error reduced, divide it by the sum of squared error for the compact model, we get R squared, and we can interpret R squared like we always do as the coefficient of determination, or if we want to, we can take the square root of it and interpret it like a correlation coefficient. And most people, I think, are fairly comfortable reasoning through like what's a big correlation versus what's a small correlation. Correlations have that nice metric that we're familiar with. Now there is one problem though, and that is that eta squared or R squared or PRE is biased. It doesn't give us the best estimate of what the effect size would be in the whole population of data. So what we sometimes do is we compute omega squared. And the formula for omega squared looks a bit fussy, but this is all information that you could get from your output from the ANOVA module or the GLM module, or indeed from the regression module. Omega squared is a bit like adjusted R squared. What it's trying to do is give us a sense of what the effect size should be in the actual population. One thing that's a little bit frustrating about omega squared is that it doesn't have that nice sort of natural metric that R squared does, and there are instead some guidelines as to what constitutes a small effect, a medium effect, and a large effect. And you can see those there, or if you were doing this for real, you could certainly Google those. The idea is similar. In fact, what I sometimes do is if I'm doing kind of a one-way ANOVA, or indeed if I'm doing a factorial ANOVA analysis, I like to do it in the regression module of SPSS, because then I just use R squared and adjusted R squared as my estimates of the effect size for the overall test. Now, eta squared, omega squared are useful as estimates of the overall effect, but often, or even usually, we care more about the effect sizes of specific contrasts, often comparisons between particular groups. So like, what's the effect size of the comparison between the placebo dose group and the low dose group, or the placebo dose group and the average of the low and high dose group, whatever it was that our contrasts were. Here, we can use information that SPSS gives us to compute a correlation for the contrast, and it's actually not that hard at all. We just use the t-statistic and the degrees of freedom that we see in our output. Again, this is really easy to see in the regression output because we just look at the table of coefficients, and we can compute a little r for the contrast and interpret it much as we would interpret any other correlation. One last thing, GLM, that is the GLM module, provides another estimate of effect size. This is partial eta squared. I'm not going to talk about partial eta squared too much right now. It's something that comes up more when we talk about factorial ANOVA, that is ANOVA where there's more than one predictor variable. But it exists, and if you ask for estimates of effect size in the GLM module, you'll get partial eta squared, which if you're only doing a one-way ANOVA is the same thing as regular old eta squared, although it'll be labeled partial eta squared in your output. Well, if we want to report these results, we might write up something that looks a little bit like this. If there's a significant effect of Viagra on libido, reporting my F statistic with the degrees of freedom. Here I'm saying the p-value is less than 0.05. It probably would be better to write out the exact p-value, or out to as many decimal places. Well, not as many as you could, but out to at least a few decimal places. It's an older convention to just say it's less than 0.05. It's probably best to be a bit more precise than that. You can see I'm also reporting omega squared as an effect size for the effective dose or drug on the outcome variable. I might also report there was a significant linear trend. Here I'm reporting the F statistic for the linear trend, giving an effect size, again, indicating that as dose of Viagra increases, libido increases proportionately. Again, that's that linear trend. I might also report, if I'd done them, planned contrast revealed that any dose of Viagra significantly increased libido compared to placebo. Here's that t-test for that contrast. You can see I'm indicating that it's a one-tailed test, and I'm also giving the R for the contrast. And the high dose of Viagra significantly increased libido compared to low dose of Viagra. And here again, I'm indicating that it's a one-tailed test. It would be better if I reported the exact p-value, or at least reported the p-value out to a few decimal places. But again, I'm giving an effect size as well there. So this is how you might choose to write up your results. Of course, it would depend specifically on what your initial hypotheses were, but this is, kind of a rough take, if you will. All right, well, it's been a short lecture as opposed to my usual ones, which are like hour plus long. Hopefully you're probably happy with that. I know I am. Next time round, I'll give you essentially the second half of this lecture, or what is often in class the second half of this lecture, and that's just a little bit of an intro to ANCOVA, and I'll cover ANCOVA in greater detail in a subsequent lecture. Okay, well, thanks so much for your time. If you're enrolled in my class, you know that the exam is coming up on Thursday. That's Thursday of this week at the time of my recording. But if you're not enrolled in my class, who knows? You probably have some other tests or adversities in your life, so be prepared for those. And when you're ready, come back for my next lecture. And as I always say, thanks so much for your attention. I really do appreciate it. Take care. Bye-bye.